So I was talking about the Heisenberg uncertainty principle in the last class. It's the slide number 5 in third lecture slide, third file in the canvas. So I just want to repeat this one. So, and we move forward. All right. So Heisenberg uncertainty principle is a kind of the observer effect. So you are doing something like this, so you are happy there, and you have one kind of mood. And if I start to observe your face very closely, precisely, your mood suddenly changes. So what was your mood before? I cannot say, right? So it's a kind of like that. So uncertainty. There is no certainty. Uncertainty principle. So the electron is moving in the orbit like this. This is the neutron proton nucleus here. The electron is moving like this. So how much is the velocity? So maybe the velocity at the beginning is a certain velocity. Without I have not been I did not observe this electron yet, right? So this electron is moving with a certain velocity. So what should I do to see this electron? Suppose you are in the dark room. So this room is dark, so we can't see each other, right? If this room was dark. So what should I do to see you in this room? I should turn on the light, right? Once the light is turned on, I can see you, right? But what happens is, in this case, so this electron is in the dark and is moving with a certain velocity. So maybe that velocity is let's say 3 multiplied by 10 to the maybe 1 multiplied by 10 to the power of 4 meter per second. So something like this. This is electron is moving when nobody is observing it. Make sense? Now I want to observe it. So to observe it, what should I do? I should shine a light here, right? Without shining the light in the electron, I can't see it, right? Now I shine the this electron to see by giving some light, then suddenly its velocity changes because this radiation gives this this electron a momentum, and this the velocity of this electron just changes from, let's say, 1 multiplied by 10 to the power 4 to maybe 2 multiplied by 10 to the power 6, something like this. Make sense? So if you try to observe the electron where it is by shining the light, its velocity suddenly changes. So you don't know how much is the velocity. So there is an error in the measurement in the velocity. Make sense? And then, but if you don't want to see it, where is the electron is here? If you don't want to, maybe the position is here. So if you try to measure the position accurately, you can't measure the velocity accurately. If you try to measure the velocity accurately, you can't measure the where the electron is. Make sense? So there are two things. So you are trying to measure the position of the electron, where it is, and then you are trying to measure the velocity of the electron by how much it is moving. So if you see, okay, this electron is right here. So you exactly measure the position. So by shining the light, but the velocity will suddenly change. So there will be large change in the velocity. So if you try to measure accurately the position of this guy, the velocity will, the error in measurement of the velocity will be more because the electron will be just changing its velocity. If you try to measure the velocity of the electron accurately, probably you don't see the electron. So you don't know where the electron, you don't know the position of the electron. Make sense? So either one. So if you try to measure the position of the electron accurately, you can measure the velocity of that electron accurately. If you try to measure the velocity of the electron accurately, you can measure where that electron is. You can measure the position of the electron accurately. Make sense? So our book gives one example here. So it's just like the mouse and light effect. So suppose you wait in a dark for sounds of mouse. When you hear the mouse, you turn on your flashlight and look at it. The mouse runs out. So you don't know the velocity of the mouse, right? It changes the velocity suddenly, something like this. Makes sense? So this is called the Heisenberg uncertainty principle. And in mathematically, they give like this: delta x is equal multiplied by delta p is equals to h by 2 pi. Something they give this. So this is the error in the measurement and position. This is the error in the velocity. Velocity is kind of the momentum. You can write the delta V also. So delta x is the error in the position of the electron. Delta p is the error in the velocity of the electron, and that number comes to be, if you multiply these two errors, that number comes to be Planck's constant divided by the 2 pi. Make sense? So this is called the Heisenberg uncertainty principle. So this equation, our book doesn't talk about this equation. So if you don't read this one, that's okay. I don't give that in an exam. You will read in higher level course. Yeah, but you need to know up to this one. So if the position is, if the position of the electron is exact, the velocity, there will be large error in velocity of the electron. If the position has a large error, the velocity will be more exact, more accurate, something like that. So if position is error, velocity is accurate. If velocity is there is a large error in measurement, position is more exact. So it's standard. That makes sense? So this is called the Heisenberg uncertainty principle. And I told you, this is kind of the very obscure, not easy to understand concept, and people just keep debating on this equation and uncertainty principle, and probably they have not come to the conclusion what really it is. Yeah, good. So let's go to another slide. It's a slide number 6. So this is the wave or quantum mechanics. So this is the quantum mechanics or wave mechanics they call quantum mechanics or wave mechanics, MECS mechanics. So there is an equation called Schrödinger wave equation. So this guy named Erwin Schrödinger, I think it's somewhere in Europe. So his name is Erwin, R-W-I-N, Erwin, S-T-H R-O-D-I-N-G-E-R. So this is the guy, Erwin Schrödinger, and he gave an equation to explain the behavior of the electrons in atom. Yeah, there are many atoms in the atoms. Right? If it's a hydrogen atom, there is one electron. If helium atom, there are 2 electrons. If lithium atom, there are 3 electrons. If that's a sodium atom, maybe 11 electrons. So there are many electrons in each atom, right? If we go to higher atomic number. So to explain the behavior of those electrons in those atoms, he gave an equation called Schrödinger wave equation. So this is the name of the guy who gave the equation. So his equation name is Schrödinger wave equation. Wave equation. So what is the equation? So equation meaning that if you have taken already the math class, something like this, right? So let's say 4x squared plus 2x plus 3 equals to 0. What will be the value of x if you solve this equation? So probably you already know in high school, right? So this kind of, so he gave something like this. So it's a very big and complicated equation in 3 dimensions. So it's not that simple. So he gave an equation, Schrödinger wave equation, and he solved that equation like how you find the value of x, right? So he find the value of x and y and z for his equation, and he started to plot in the graph. Yeah. So he started to plot in the graph. So he got the value. So from the Schrödinger wave equation, he got 3 values like x, y, z. So maybe x comes to be 1, y comes to be 1.5, and z comes to be 1.8. So he started to get something like this. So he had a big equation in terms of x, y, and z, and he solved that equation, and he got the values of x and y and z, and he plotted those in in the plane like this. So this is x-axis, this is y-axis, right? So you know how to plot the graph, right? So you already did some graph plotting in, I think in the lab number 2, and you also did some graph plotting in lab number 3, and you also did graph plotting in lab number 4, right? So you did a lot of graph plotting. So he started to plot those graphs. So when you plot those graphs, so what what kind of solution he got it is like this. So so one time when the electron when he solved that equation and plot the graph, so he got something like this, something many point like this. So he got many point like this, and he plotted here. Make sense? So maybe this is a x, this is a x and y value. X maybe this is 1, but y is 0, and here it has a z value. So he started to plot in the graph in the in 3-dimensional form. Yeah. So you take a point here and then put x value and the y value and z value, and you get 1 point, and you get another point, you get another point, right? So many points he plotted, and he gets something like this. It's a sphere. Make sense? So first of all, he gets something like this. So when he plotted many value and he looked at what kind of the data point he got like this. So this is a sphere. So maybe, I don't know if you can see here. So this is a sphere. So he got something like this. This is a sphere. Yeah? It's not a plane. XY. There is a Z axis also. So he got something like this. Make sense? So, and then this is for the n is equals to 1. So he solved this equation for n equals to 1, meaning that, so this is the atom. So you have a neutron, proton here. You have a first axis, a first orbit here, n equals to 1. So for this one, for n equals to 1, he solved this equation and he got the point like this, and he plotted here, and it just looks like this. Make sense? Then one sphere. Now this is n equals to 2, and he solved the equation for the n equals to 2, and he got like this. So exactly same here. So he started to get bigger value here, like this. So bigger ball like this. He got like this, n equals to 2. Make sense? So, and he solved the equation for n equals to 3, n equals to 3, and plotted the data point, and his data point looked like this, like this, like this, like the big ball. Make sense? So what it means is that if n is equals to 1, the electron doesn't remain in one orbit as said by Bohr. So Bohr was saying electron is remaining in just one place here, right? In one orbit, at one place, and it was moving like this. But what Schrodinger showed is that no, it's not. The electron don't behave how Bohr said. So it behaves like this. So kind of this one. So this is a sphere. So in this sphere, maybe the electron is here, maybe the electron is here, maybe the electron is here, maybe electron is here, like this. It's a sphere. I can draw this the three-dimensional in the board, but it looks like this. Make sense? So there, like the soccer ball, you have a soccer ball, and at the center of that soccer ball, imagine there is a nucleus, there is no electron, and from that nucleus outside all that sphere, there is a probability of finding the electron. Make sense? So that's how he did. So like this, and then so when he solved the equation for the n is equal to 1, so he looked like this. So what I'm saying is this is a proton, neutron here, nucleus. So n is equals to 1. So when he solved his equation for n equals to 1, he got a sphere like this. So this is a nucleus, and there is a probability of the finding electron within certain distance from this nucleus, like this. At one point, electron can be everywhere inside that sphere. Where electron cannot be? Electron cannot be in the center here. Electron cannot be at the nucleus. So his equation says that electron cannot be at the nucleus, and there is a sphere of certain radius like a soccer ball, and the electron can be found everywhere. So it's not in sitting at a certain distance. So it's jumping around within that sphere. Make sense? So that's why n is equals to 1. So how does it look like? So it looks like spherical, right? A sphere, like the ball, soccer ball. So he gives this name as a S, spherical. Make sense? So if he got the solution like this, he give the name S. And since he was solving the equation for this n is equals to 1, so he told us that, okay, 1s. So this is 1s. Yeah, make sense? So he got this one. Now, another time he was solving his equation for n is equals to 2, bigger circle, bigger house, right? So n is equal to 1, we are done. So this is only one s orbital for the first orbit. Now we call the orbital. These are called orbital. So where is the maximum possibility of the finding electron is within this distance from the nucleus to certain radius and within that ball. Make sense? Good. Now he solved his equation for n is equals to 2, and he got 4 solutions. So let's see. So this is 1 is done. Now for 2, n is equal to 2. So he solved equation and he found like this. So this is x-axis, this is y-axis. So he got a bigger ball like this. It was smaller, now it is a bigger, right? So he got something like this. And where is the 2s electron? Finding the 2s electron. So the 2s, this is the nucleus, and you can find that 2s electron everywhere, not in the nucleus, but you can find every other places. But there is a place where we'll talk later where this electron will spend most of its time. But let's talk at this moment is that the electron for this second orbit, the electron cannot be found in nucleus, but it can be found in the places everywhere except the nucleus, but further distance from the one is like so. So this is like the concentric ball. So this ball is within this ball. Make sense? Yeah. So imagine that there are 2 balls. So there is a small ball inside the bigger ball, and the first electron, the first orbit electron is just moving within this distance. So we are just putting this here. We have a second orbit electron, and that sometime come here within this region, and sometimes is here, and just we can find everywhere that electron. Good. So this is one solution for n is equals to 2. Now, so this one is spherical, and it is coming from solving n for 2. So we get 2s. So its name is 2s. Why 2s? Because he solved this. He got these points by solving his equation for n is equals to 2, and it's found to be spherical, and so that's spherical and for 2. Make sense? 2s. Now he started to keep solving his equation, and another time he found for this one n is equals to 2, he found space like this. So he put his data point, and one time he got something like this. He got this data point for one time, and another time he get this data point and plotted this, and this space looks like this. Yeah, and another time he solved his equation by putting different values. The equation, the spherical, the shape come like this. Another time he solved that and by putting other values, and he got the different values and got like this. So this is x-axis, this is y-axis. So this one is like this. So this is 2s, right? So this is 2s. From n is equals to 2, he got a value like this, 2s. So like this, the ball, like this one. Yeah? So that's a 2s. Now another value he got like this. When you plotted the data point, it's called the dumbbell, like how you lift your dumbbell like this, right? So while you do the exercise. So he got the value like this. So it's along the x-axis. So he give name this as a px. So the electron can be that electron can find maximum electron can be found here or here or here and here, but you cannot find those electron in the nucleus part where you handle the dumbbell. Make sense? Good. So this one like this. Now another equation exactly same size. So another like this. So how you hold if you hold the dumbbell like vertically like this, so electron can be found here, but where I am holding the dumbbell, you cannot find the electron right here in my finger. Make sense? And then this one is so like this one. So hold the dumbbell like this, and it's like this. So you can find it that n is equal to the second orbit electron in this region, but you cannot find the electron where you can where I am holding this thumb. Dumbbell. Make sense? Good. So if you put these three orbitals together, it looks like this inside the atom. So like this one. So you see. So where is the center is here. There is a center and there is a s orbital. So this is a s orbital for n is equals to 2 here at the center somewhere around this one. And this one is a, if you hold like this one is a, we call PZ. This is PZ. So this coming up and going down is called PZ. This going this way and going this way. This is called PX. And this is going this way and this is coming toward you. This is called the PY. So it's a little bit difficult if you draw this in. So it is easy to visualize this one and this one. It's going up and down. So it's going up and down. You can know it. It's easy to visualize this one going this way and this way. This x-axis is easy. But you can't visualize this one and this one. So this guy, so this one and this one. One is coming toward you. One is going away from you. So this one and this one, you can't imagine. Yeah. So this is Py. Make sense? So these are the orbitals for n is equals to 2. So if there is a electron in the second orbit, sometime that electron may jumping around in the circle like the sphere like this, or maybe that electron jumping here, but not here, like this. Or if it goes toward the x side, it's jumping like this way. Or if it plans to jump like this way, it jumps this way and this way. So this is called the orbital. So where is the orbital? Is the probability of finding the electron around the nucleus. Make sense? So would that electron found here? Here? No, the electron cannot be found there. Outside this region, you cannot find that n is equals to 2. When this electron cannot be found outside this region. Cannot be found outside this region. Cannot be found at the center. That electron cannot be found in the center here. It cannot be found outside this boundary. So here you cannot find that electron. Only you can find that electron here and here. Only you can find those electrons here and here, and only you can find those n equals to 2 electrons like this. Make sense? So these are called the orbitals. So probably this is the hardest thing in science so far people have studied. Yeah, good. So this is called the orbitals. So what are orbitals? Orbitals are the spaces. Orbital comes by solving the Schrodinger wave equation and plotting those of that equation in the three-dimensional form like this, and they represent where is the maximum probability of finding that electron around the nucleus. That's the probability. It gives the probability. Yeah. So they are called the orbital. How does it come? It comes by solving the Schrodinger wave equation. Good. All right. So, and then when we solve this Schrodinger wave equation, we get spaces like this, and we give these names. So this is like this is 2s. Now this comes by solving the n equals to 2. So this is also 2. This is also 2. This is also 2. So this is along the x-axis. This is along the x-axis here. So he gives 2px here, and this is along between the xy. So sorry, this is between the xy, they call it z. So one is going away from this board, one is coming toward you. I already showed you. How does it, this one? This is not like this. So this is going this way, this is coming toward you. It's just, look here. So like this. So if you put this all together here, so this would look like this. So this one is a py, this one is a px, and this one is a pz, like this. So this one is going up like this one is coming down like this, and then this one is coming this way, this one is going this way. Now this one and this is going away from the board, and this is coming toward you like this. So if you put these three orbitals together, they look like this. Yeah. And where is the 2s? The 2s is somewhere here, around here. That one. Make sense? So he did something like this. I don't know. So his equation shows something like this, but does electron actually work like this? I don't know. All right. So now these are called the orbitals. If you solve this equation for n is equals to 3. So let's say this is neutron proton and this is the first orbit. So first orbit we have already solved the equation. Second orbit we already solved the equation. Let's talk about the third orbit. He solved his equation for n equals to third orbit. And he got the value so bigger than this one. So 2s was like this, so he got another value like this. So like the big sphere he got. So now he gives this name as 3s because this comes by solving the n equals to 3, right? So he gives the name 3 and it's a very spherical. So he told, oh, let's give this spherical or sharp or something like that. And then this also comes to be bigger for 3. So let's say this is a p, this is in z axis, this is in y axis here. So he gave the name py for like this, but it is a bigger. So now it's a bigger like this for 3. Now it comes by solving n equals to 3. So he gave name py, 3py. Now this also comes to be very big for 3 like this, very big, and then he gave 3pz, something like this. And this one is a 2px. So that for 3, this lobes comes to be bigger like this. Just we are repeating the same. Make sense? Good. So exactly the 3. So 2px. Sorry, 2px. These two lobes are 2px. These are 2py. Sorry, this is 2py where I am holding. Now this is 2pz. But for 3, this lobes is bigger here up here. Yeah. So bigger up here, bigger, all sides bigger, but exactly same. Make sense? So 1s is tiny inside this this center, tiny there is a sphere. The 2s is a little bit bigger there, and the 3s is a little bit bigger. All are within the same atom. Make sense? So like this. So this is how these orbital concepts come here. So if something is very close to the nucleus, they have the very small energy. So let's say if you calculate the, you already know that this thing. So how about the energy? So if the sphere is very small from the nucleus, the electron has very small energy, right? We already talked in the previous Bohr concept, just like that. So this electron has very small energy. So it's the 1s. So electron is in the kind of the and it's jumping around everywhere there except the nucleus. And then 2s is a big one like this. This has bigger energy than this case. And for 3s, like even bigger energy. So 1s is small energy orbital, 2s is bigger energy orbital, 3s is even bigger energy orbital because electron is jumping far from the nucleus. Make sense? So same, 2px is higher than 2px, 3px. Now which is higher energy? This is a bigger orbital. 3px is like, so this is a 3px. Let's draw the orbital here. 3px looks like this. Very big, 3px. But 2px just looks like this. 2px looks like this. So, which has a larger energy? This guy has a larger energy because the electrons come from this center to all the way up here. If the electron can jump further from the center, that has a higher energy, right? So, 2px has smaller energy, 3px has higher energy. Same as like the 2py. 2py has energy like this. Let's say 2py is like this, so small energy, but 3py is very big, like this. So this orbital has larger energy. Electron is far from the center. Make sense? Good. So that's how they do this kind of thing. And unless you do the research in PhD or further, you will understand probably this one. Otherwise, that much I can understand. I never solved the Schrodinger equation myself, so I really don't know how the points look like. But in masters in the higher level, they teach one course in quantum mechanics, and they try to solve for the 1s up to 2s. They don't teach to solve n equals to 3 or n equals to 4, n equals to 5. So that's that. All right. So now the quantum number comes from there. So now let's talk about the quantum number. So basically, how I just told you is they come the numbers called the quantum number. So this 2px, 3px, 2py, 2py, 1s, 2s, 3s. So they call this number is a quantum number. Yeah. So the quantum number shows where is the electron and which electron we are talking about. So just like this one. Now, if I want to identify one person from this room, I need to go this way, and I need to move from here to here, and then in which coordinate I need to move to find a certain person. It's like the address of the electron. Yeah. So it's just the address of your house. The address of the electron and address of your house is exactly the same thing. Yeah. Good. So the quantum number basically says which electron we are talking about. So now let's talk about the quantum numbers. So where does the quantum number come? I just showed you where the quantum number come, right? 1s, 2s, 3s, 3p, 2px, 3py, 3dx, whatever different kind of the species. By solving the Schrodinger wave equation, those number comes, and they are called the quantum number. So what do quantum number tell about? It tell about the address of the electron. Which electron we are talking about? There are millions of, there's hundreds of electrons in different atoms. So we are talking about the address. Which electron we are talking about inside the atom that it tells quantum number. Make sense? So the quantum number is a number that tells the address of the electron, the particular electron. So let's talk about the quantum number here. So there are 4 quantum numbers. So one is called n. It's a principal quantum number. Principal quantum number. Principal quantum number. Quantum number. Principal quantum number. Which electron, which orbit we are talking about? So let's say this is a neutron proton. If we are talking about the first orbit electron here, we give the n is equals to 1. Yeah? The principal quantum number. If we are talking about the second orbit electron here, we give n is equals to 2. N is equals to 2. For this electron, the first, like this is the grandfather name, right? Grandfather name, like that. This is the grandfather name. And then for this electron, we give n is equals to 2. And for if the electron is here, we give this as n equals to 3. First, we assign the first name, like the grandfather name, right? Now we need to define another name. It's just like we just define the country. Which country is in? Which state? Which state is in? Wisconsin. This is in Wisconsin, right? And which state this is in? Illinois, the second one, right? And where is this electron? Which state is beyond the Illinois? So maybe Ohio? I don't know. Below Illinois, this is Ohio, right? So we just got one address here. Make sense? So if the electron is 1 in the first orbit, we give n is equals to 1. Because it's very close to nucleus, just like Wisconsin. We are in Wisconsin. And then if the electron is the second, so the state joined to us Illinois. So if somebody is sitting there, we give this guy's address is in Illinois. And from below the Illinois, maybe Ohio, n is equal to 3, right? And below the Ohio, maybe, I don't know which one, maybe n is equals to 4. What is below? So there, so further and further. Make sense? So we just got state. Now we need to find the street, right? Now state is not enough to define a person address. Now we need to find the street also, right? So just like that. Now imagine a house. So let's say this one, n is equals to 1. So they say that if n is equals to 1, you don't have to give the street name. So we are in Wisconsin, we are good. Or we are in this class and we are good. So I'm teaching here, so everybody knows me what this guy teaches here. So it doesn't have any further quantum division. So this cannot be divided further, and they give, so this is one level. Now this we cannot divide further. So So imagine like this is the house here. So n is equals to 1. N is equals to 1, and it cannot be divided into further smaller parts. So they give this as a that's L. L is equals to 0. So just like that, they give that like that. So there are 4 quantum numbers: N, L, M, and S. So four things we need to give. So this is the house. The electron is in this house. So the quantum number N is equals to 1, and this cannot be divided further. So this is just 0. So if this is 0, M is also 0, and S can have plus half and minus half. I will talk about that later. So there is a one house here, and the house number is 1. So you cannot cut this house into smaller. So if somebody want to rename it, they give this as a okay. N is equals to 0. So this is called azimuthal quantum number. And if they want to give further quantum number to this one, you cannot divide this house. So M equals to 0. So everything within this is N equals to 1. So somebody name this as 1. Somebody may name this as L equals to 0. Somebody may name is ML is equals to 0, or somebody may now comes up to here is the naming of this house. Now there may be electron. If the electron is here, 1 electron, you can say okay, this electron is spin quantum number is plus half. It is moving like this is the electron, and this is spinning like this one, like in own axis. So how the Earth is rotating is in own axis. So here is the axis, but the electron may be spinning this way, or the electron may be spinning this way. So let's say the electron is spinning this way, plus half. And if there is another electron in this house, this must rotate this way. Both electrons cannot move, cannot rotate in the same way. Make sense? So if you are a roommate, if you are alone, you can do whatever you do in your apartment. But if 2 people are sitting, living together in a room, you must adjust according to friend behavior, right? Just like this. So this is moving, this is rotating this way, this is must be rotating this way. So if the name of this guy is ms is equal to plus half, the name of this guy will be ms is equal to minus half. Make sense? Good. So like this. Now let's talk about the n equals to 2. So we have 4 quantum numbers. They are N, L, M, and S. So MS. So 4 quantum numbers. So this is either plus half, another must have minus half, and then this number we are trying to find out. Now we just finished the n equals to 1 house. Now let's do the n equals to 2 house. So the n is equal to 2 house is, so this is a neutron proton here. This is n is equals to 2, bigger house, right? Bigger house. Now let's say this bigger house is like this. This is a big house. N is equals to 2. Somebody give this name as a n is equals to 2. N is equals to 2. Yeah. Now you can cut this house into 2 parts. Because you have n is equals to 2, what is the number then? Because previously there was a number 1, so I could not cut that house as into smaller. There was a n equals to 1, so I didn't cut like this. So now this is n equals to 2, bigger house. Now you can cut this house into 2 parts. Make sense? N equals to 2. Cut this into 2 parts like this. Yeah. So give 0 to first. Always we start to give from 0, and then give another 1. So just like this is a room, this room name is n equals to 2. So I cut this room into 2 parts, and the first one I give the 0, and the second one I give the number 1. Make sense? Good. So this S, this 0 is called S. S, 1S, 2S, 3S, right? So we are working with the 2, so this is 2S. So this is, give number 0 to this one. Now this is, 1 is called P. 1 is called P, or 2P, 2PX, 2PY, 2PZ. So cut this one house, you can cut here. Now you cut this one house into, so that's, I am cutting 1 here. So I cut this house into 3 parts like this. So this is 0, this is minus plus 1, this is minus 1. So that's how we derive the quantum number. Yeah. So this is the house number 2. House number 2 here. So I cut this house into 0 and 1 first, 0 and 1, because I cannot go up to 2. So 0, 1, 0 and 1, 0 and 1. Yeah. Now 0, I cannot cut this into other part, but this 1 can be cut into 3 parts. So like 3 parts, and then this is the number 1. So we give the number is 0 minus 1 plus 1. So there was this house name was 1, and this can be cut into 0, plus 1 and minus 1, like this, 3 houses. So if there is 1 electron will be here. 2 electron, if there are 2 electron will be here. Maximum number of electron, 2 electron can sit here, like a 1 room, 2 people can sit here, 2 people can sit here, 2 people can sit. If there is 2 people are sitting here, one is rotating like this, another is rotating like this in the axis. Make sense? So that's n equals for n is equals to 2. Now let's plot that n is equals to 3 house. So if the electron is in the third orbit, let's say electron is in the third orbit, so third, n is equal to third. So this is neutron proton nucleus here. So first orbit, second orbit, third orbit. So this third orbit, how can, if n is equals to 3, the electron is here, how can we give the quantum numbers to n equals to 3 electrons? So just like this. Imagine that there is a big house like this, big house. This is not, the name of this house is n equals to 3. So somebody give n equals to 3. Yeah. Now cut this into, how many parts you can cut into? 3 parts, because number 3. Previously n equals to 2, I cut those into 2. Right? Now it's n equals to 3, I can cut these into 3 parts. 1, 2. 1 room, 2 room, 3 room, like this. Make sense? Now what is the name of this one? The first is 0, the second is 1, the third is 2. Make sense? Third is 2. Now, so 0 is called S, 1 is called P, 2 is called D. Then they're naming, they name like this. If you want to give the numbers to identify those, they are 0, 1, 2. But if you want to give the letter to identify those, they are S, P, and D, like this. Yeah, and then this one you cannot cut further, but this one you can cut into 3 parts: 0, plus 1, and minus 1. So 0, plus 1, and minus 1. So like this. So this is 0, plus 1, minus 1. So they give this as a px. One is ps, another was py, another was pz. Just like how we derive this px, py, pz, right? Now, how about this g equals to 2? Now you can cut this into even further. So this is n equals to 2. Now I can cut this house from minus 2 to plus 2. So like this: minus 2, minus 1, 0, plus 1, and plus 2, like this. So this 2 can be cut into 1, 2, 3, 4, 5 room. 2 can be cut into 5 room. 1 room, 2 room, 3 room, 4 room, 5. 1, 2, 3, 4, 5. So you can give the equal there. So if you give minus 2 here, this is minus 1, this is 0, this is plus 1, this is plus 2. Yeah? Good. Here you can give px, py, pz. So these are the d. N equals to 2 is d. So we give the name d. So you can give, okay, this is a dx, y, dxz, dyz, dx square, y square, and then dz square. So they give the name like this. Yeah? We'll practice this quantum number, how to derive. So I'm just trying to explain you how to come those numbers. Yeah? How to come to those numbers. Good. So like this, n equals to 3 can be cut like this. So where is it in the third state? So Ohio. And then where is the electron? Maybe in this state, or maybe the second state. And if the second state, which house? Maybe this house, or maybe this house, or maybe this house, right? Or maybe in the second another state. So which house? This house, this house, this house, this house, this house. Just like the where is the electron, or where is the some person we are trying to find. Make sense? So that's how we got those those orbit to give the quantum numbers. Now, how much time I have? I have 5 minutes time, so let's see. Let's practice couple of quantum number here then. So how many quantum number we have? We have 4 quantum number. So I make a table here, and so let's say electron is a number n equals to 1. So first orbit, where is the electron? In the first orbit, right? Now, first orbit can be cut into smaller? No, first orbit cannot be cut into smaller. So L, it is called azimuthal quantum number. I cannot cut this first house, so I just give L is equals to 0. I cannot cut into. So then go to the, I further try to cut it. Can I cut this further? I cannot cut. So this is called magnetic quantum number, and it is 0. And now in this house, maybe there are 2 electrons. If one electron is rotating the right direction, the another electron must be rotating like this. So Ls can be -1. So for n equals to 1, this is the possibility of the quantum number we have. Make sense? Good. Now let's do n equals to 2. The quantum number for n is equals to 2. Let's say electron is in the second orbit, n is equals to 2. Maybe now this n is equals to 2 house can be cut into many, I mean, at least this is n equals to 2 house. So you can cut this into 2 parts, 0 and 1. And then 1 can be cut into 0 plus half, plus 1 in -1 like this, right? So L is equals to the azimuthal quantum number. It can be 0 or it can be 1. It can be 0 or it can be 1 like this. It can be 0 or it can be 1. You can cut one level there. Make sense? Now this one you cannot cut further. So for this one is for ml. For this one, if the number is coming from this one, ml is just 0. ml is equals to 0. But this house, L is equals to 1 house can be cut into +1, 0 and -1. So from here, I can get number plus half, sorry, +1, 0 and -1 from here. This number coming from this guy. This number is coming from this guy. So the electron can be in here. So that may have a spin value. Maybe it's rotating plus, or it may be rotating the minus. Maybe it's rotating the clockwise, or it may be rotating the other way. So if the electron is there, so the electron is maybe rotating positive or another direction. Electron can be here, can be rotating clockwise or anti-clockwise. Electron can be here, like this. 1, 2, 3. So one electron can be here, maybe rotating like this, or it may be rotating like this. If there are 2 electrons, one is rotating like this, another is rotating like this. So if one electron here is here, maybe it is rotating like this, or maybe it is rotating like this. But there are 2 electrons here in n equals to, let's say this is a -1 house. If one is rotating like this, another must be rotating like this. Just like that. Make sense? Very complicated concept. Yeah? So they did something like this. So what is the name of this one? So if you want to, so it's 48. So L is equals to 0. If L is azimuthal quantum number L equals to 0, they give this as a S, and they give this one as a name T. Yeah, and this one ML is a I don't know. This has a name, but this has a name. Maybe this is a PX. Maybe this is a PY. Maybe this is a PZ. Like this. So this one, the house of this guy looks like this. The house of this guy may look like this. The house of this guy may look like this. Just like let's imagine how kind of the house of the electron. Yeah. Alrighty. So I think I did something. So maybe you did a couple of time and you could understand. So this is the last thing in this chapter. So we will practice some quantum number, how to do quantum number. Repost the recorded lecture. I always put the Canvas lecture in the recording in the Canvas. So you just click the 3 line above this course. And when you click 3 lines, and there are you see the button recording, and click those, and there are many videos. Make sense? All right, thank you very much.